Okay. So, what we have done so far is means discussion of FM and its noise analysis. So, we have also proven that in presence of noise, FM performs better in a way that we have also shown that FM is probably the only modulation scheme where we can actually exchange the bandwidth efficiency with the noise performance. What does that mean? That means if we increase the noise bandwidth, if you increase the FM bandwidth, that means make a wider band FM, that is what we can do. If we do that, immediately we can see there will be a positive effect in terms of noise cancellation. Okay, so more wider the FM bandwidth, better noise characteristics will be able to see. So, this is something which has been already proven. We have also done that for a tone modulation. We have shown how better it is in terms of noise cancellation with respect to AM, and what parameter set like the modulation index, which is directly proportional to the FM bandwidth or frequency deviation. So, how we can set that to make it better than AM. So, this is something we have already demonstrated. And at the end of last lecture, we could also show that and even before also we could show that FM has a noise cancellation or even interference cancellation when the interferer signal is closer to FM signal. So, this is something which has happened, and especially that was proven that FM noise due to the demodulation process looks like this. So, basically the noise spectrum or power spectral density looks like this, if this is minus Bt by 2 to plus Bt by 2. So, that is something we have already shown. So, what effectively we mean by this, that if this is the FM carrier and around which the FM modulated signal is there, so something closer, either noise or interference, very closer to that central frequency of that FM modulated signal, that will be cancelled out. Whereas, as we go away from the central frequency, the noise power spectral density also gets boosted up, as well as interference also we have seen that. That is something which is to be noted for FM. So, this is typical of FM. Now, generally what will happen whenever we within this there will be means this is the low pass equivalent noise characteristics, right. So, if I just plot the signal spectra, that should look like this. Okay. So, this is my MF power spectral density or power spectral density, let us say SMF, okay, with respect to frequency. Okay. So, we know that it is band limited, probably that is the band. So, minus W to plus W, and of course, W must be less than Bt by 2. So, that is a condition which generally happens, we have already shown that. This Bt is actually the actual FM bandwidth, whereas W is the message signal bandwidth. So, FM bandwidth is always greater than that W, that is something we know. So, what happens in this side at the higher frequency, generally the message signal shows that it is because it is band limited. So, the spectrum component will be having lesser amount of power. Okay. And whenever it is transmitted after the receiver, the discriminator circuit followed by a low pass filter, what we will see at this position noise is more enhanced due to FM demodulation, and this is the point where signals are means having less power. So, if the signal is having at this frequency, of course, overall we have already analyzed, but at this frequency we just concentrate on the higher side, higher frequency side of the message signal or message band, we can see the noise power is higher, whereas signal power is lower. So, maybe something can be done over here. Okay. So, what is that something? The something is like this. See, noise is getting added at the channel, right, that has nothing to do with the transmitter. So, I have a transmitter followed by channel through which it propagates, this is where noise gets added, and followed by a receiver. After that I get my signal as well as noise, okay, the composite part of it. So, this particular noise after going through means added in the channel and going through the receiver, that looks like this. Okay. Now, I can do something to the signal. What I can do is effectively, because I know that noise will be already higher at the higher frequency. So, I can deliberately boost the signal at the higher frequency. Okay. That boosting will not boost the noise, because that boosting will be done at the transmitter. So, which is independent of noise. Before even noise gets added, I boost the signal. So, that signal is already of high power, then the noise gets added. Due to the demodulation process, noise will be as it is, but the signal has been already boosted at the transmitter side. So, at the receiver side, signal will have that boosted things. Now, what we have to do, of course, the signal, if I boost it, the relative amplitude at different frequency level has been changed. So, basically that will distort the signal. So, if I have boosted it, I need to put a de-booster or some filter which is just cancelling out this boosting at the receiver. So, the fun begins when I start putting that. So, if I start putting that, so suppose I have a receiver, after the receiver I put that reverse thing, at that time what will happen? The signal, it will come back to original, but because this is actually reducing the overall amplitude or overall power of the high frequency term. So, what it will do to the noise? Noise is as it is, because it has not gone through some boosting. So, it will be as it is. So, here if we are de-boosting it, or if we are reducing the amplitude of the high frequency part, so noise will go through that reduction in overall power. So, at the output I will see the same signal, because it was boosted at the transmitter. So, before transmission I have this boosting, and here it is the reverse operation. So, I will get the same signal, but this noise power will be much more reduced. So, this is a technique which has been employed in FM, which helps means combating noise even better. Okay. We will probably show with a practical almost first order this boosting and de-boosting filters, which are called as pre-emphasis and de-emphasis, because we emphasize the higher frequency before transmitting, and de-emphasis is just doing the reverse. So, pre-emphasis then de-emphasis. So, we de-emphasize it and bring it back to the original after the transmitter. So, this pre-emphasis de-emphasis actually gives you, with the practical implementation of pre-emphasis de-emphasis, will be showing that almost 30 dB gain in terms of signal to noise ratio. Okay. So, means 13 dB. Okay. So, that is what we want to achieve. Let us see how that can be done. Okay. So, the overall thing is there should be a H pre-emphasis or pre-emphasis just before the transmission. So, our message signal MT must go through this, and then followed by whatever FM transmitter we have, any transmitter is okay, and then it goes to the channel where the noise is being added with the modulated signal, modulated pre-emphasized signal. Okay. So, then I go to the receiver, which is FM receiver. Okay. Followed by, of course, I have to cancel that pre-emphasis. So, I have to put a H de-emphasis filter, and that should be my transmitter receiver chain. And what we should also realize that this HPEF into HDEF, this must be 1, because they should just cancel out each other. Okay. So, whatever the transfer function of the pre-emphasis, de-emphasis must have inverse of that, so that they just cancel out each other, and the message signal passed through this chain of pre-emphasis and de-emphasis will actually have the same quality, spectral quality as well as time domain quality. Okay. So, this is something which has to be happening. Okay. So, if this is the part, then let us try to see after the receiver, okay, after going through de-emphasis, what should be my signal and noise. Signal should remain as it is, as we have discussed earlier, but the noise part will go through this. So, basically we have already told that this NDF is the noise power spectral density at this point. Okay. So, that goes through the de-emphasis filter. So, it must be passing through the de-emphasis filter, and that is what the noise will be. So, if I just at the output, if I wish to get SNOF, that must be passing through a filter. So, which is also pre-emphasis de-emphasis will be means proving that they are generally chosen to be linear time invariant. So, I can again put that whatever random process theorem we have proven, that any random process with a power spectral density, if it passes through a particular filter which is linear time invariant, then the output power spectral density will be the input power spectral density into mod HF square. So, same thing will be happening. So, if this is that HDF DE, so that must be H capital DE sorry F square S NDF, which was the noise power spectral density over here. This is that part which we have already derived, that looks like this, right. So, and that is defined from minus W to plus W, right, because this is after employing the low pass filter also. This is the entire sorry, it should be FM. So, entire FM demodulation chain. Okay. So, that is after the demodulation and after following, means after putting the low pass filter of the message bandwidth. So, that should be the noise spectral density. Okay. So, this is what happens. Now, let us go back and try to see what is the overall noise power, okay, and what we will try to evaluate, that what is the relative benefit by doing this de-emphasis. Okay. So, let us say I have this particular thing which is defined. This is actually average noise power without pre-emphasis de-emphasis. So, this is without pre-emphasis or de-emphasis filter, and the ratio of average noise power with pre-emphasis de-emphasis filter. So, I am just trying to see if I means put this pre-emphasis de-emphasis, what will be the noise power at the output, provided that same kind of message signal and same kind of noise is being added in the channel. If I do not put it, what will be the output noise power? So, I am just trying to take the ratio of this. This will be the improvement, because the signal power remains the same, only the noise power will be reduced by this factor. Okay. So, this is something I am trying to calculate. So, what will be the noise power with pre-emphasis de-emphasis? So, this is with PD. So, that must be, we know already this relationship SNDF HDEF square. I have to integrate it from minus W to plus W, right. It is valid from minus W to plus W. So, all I have to do is that only. So, if I just do that, we have already derived the noise power spectral density as NDF. So, let us put that. So, that was equal to N square by S square F square. Now, along with that there will be a multiplication term of HDEF, right, and this must be integrated. So, that is the overall power spectral density. This was the power spectral density for NDF and that SNDF, and multiplied by this square, then I have to integrate it from minus W to plus W, right. So, this should be my overall this one. And what has happened for noise power without PD, we have already calculated. So, that should be noise power without PD. This is something we have already demonstrated. So, that is just minus W to plus W N0 S square F square DF, right. So, this is something we have already evaluated. So, to get I, we have to take the ratio of these two. So, therefore, that I should be, after doing all this calculation, what we will have will be having, so without one on the top and with bottom. So, that should be this. So, this should be 2 W cube. So, after doing this simplification 3, and I will be only left with this integration F H D E F mod square D F. That is my I, right. So, N0 AC square gets cancelled because this is a ratio of noise power. So, I will be just I have to evaluate this. Okay. So, let us try to see if we have a practical filter for this pre-emphasis and de-emphasis, how do we, means what should be the performance. Okay. So, let us say we employ a pre-emphasis filter which is almost, which looks like a high pass filter, because I want to really, pre-emphasis means the higher frequency I should boost and lower frequency should have means they should be suppressed. So, if I put a practical high pass filter which has a nice means smooth slope, something like that. So, it will actually boost this higher part and it will means reduce the lower part sufficiently, right. So, high pass filter, if we just give one example. So, this is C, small r, and followed by, of course, we have to amplify it also. So, R, and that is the amplifier, that is the input impedance of the amplifier. Okay. So, this is that high pass filter part. Okay. So, if I just put my message signal over here, whatever at the output I will be getting, that is actually the pre-emphasized message signal. Okay. What is the corresponding transfer function? So, we have to also consider that this r is much lesser than this small r. Okay. So, that is something we will have to ensure, and also the cutoff frequency, this 2 pi f c r, that must be much less than 1. So, it must be much lesser, means this particular overall thing, okay, that C and R. So, this is, these two things we have to ensure just to make the high pass filter, so that at the lower band also it is passing something, otherwise the message signal will be completely suppressed. So, I do not want that. So, I just want to emphasize the higher frequency part. So, it will definitely, what I will try to do, the high pass cutoff frequency I will bring it very close to 0, means it should be closer to that, so that the higher frequency is getting little bit amplified, or means, and the lower frequency is getting a little bit suppressed. So, this is something which is happening, not completely getting suppressed. Okay. So, I do not want a high pass filter which is like this. Okay. So, then the lower frequency, which is the actual message signal, will completely be gone. So, I do not want that. So, that is why this restriction I will be putting, and accordingly the HPEF should look like 1 plus JF divided by F0, where F0 is 1 by 2 pi CR. Okay. So, this is just that filter characteristics we are putting. So, if HPEF is this, immediately HDEF becomes 1 by that. So, 1 by 1 plus JF by F0. So, of course, that should have a reverse characteristics, and fortunately that can be realized. So, if we just put R over here and C over here, so it is the reverse thing, low pass equivalent part. Okay. And if I just put that, this will have a transfer function. If you try and look at your filter designing skills, you will be knowing that that should be the transfer function of this particular filter. So, we have already designed HP and HD, and that condition that this multiplication must be 1, that is being satisfied. Okay. The way we have taken the transfer function, and it is, as you can see from the filter, these are all first order filters. Okay. So, be it high pass, low pass, these are all first order filters. So, if we have this, then can we now calculate the I? Okay. So, that I, which was we have derived, the formula is this. Sorry, in that formula I think we have missed something. So, earlier when we have shown that square was missing, so it should be F square HDEF, right. So, that must be the overall thing, and now just put that filter HDEF, you already know. So, if I just put that filter transfer function, so I get minus W to plus W F square DF divided by that filter characteristics mod HDF square. So, that is F by F0 whole square. Okay. Now, it is just doing this integration, which is a simple integration. So, this can be means you can separate them out and you will get tan inverse integration. So, if you just do that, it will become finally I am just giving the final form. So, that should be W by F0 minus tan inverse W by F0. Okay. So, this F0 has to be manipulated. Okay. It should be written as 1 plus. So, here F is there, take F0 out. So, this will become F0 minus F, and then this plus 1 minus 1. So, this plus 1 that gets cancelled. So, this will be just df integration. So, that will be f, which gives you this minus 1 by 1 plus f by f0. So, f by f0 you substitute with some variable, and then do that, it will be just tan inverse this. Okay. So, that we know already, that is a simple method of doing it. Okay. So, this is what is happening, this is becoming I, and if we just take F0 to be 2.1 kilohertz, and if we take W to be 15 kilohertz for a typical FM transmission. So, you must be seeing that this is not just voice, this is actually a whole band of even musical instruments also comes under this. So, 15 kilohertz means voice was just 3.4 kilohertz. So, this is actually a wider band message signal, okay, which includes as well as means voice as well as some musical instruments which has higher frequency component. So, if that is the case and we choose F0 to be 2.1 kilohertz. So, it depends on what F0 you choose, because we can see already this I is function of F0. So, if we choose this thing, then immediately I becomes 22, and in dB terms that is 13 dB, that is what we have told, that in a practical FM case we can actually reduce the noise. So, this becomes 22 times higher, that means without this thing pre-emphasis de-emphasis, whatever noise we get, that is 22 times higher than the things with pre-emphasis de-emphasis. So, basically 13 dB higher noise you will be getting at the receiver if you do not employ pre-emphasis de-emphasis. So, that is a big benefit. So, SINR will be accordingly you can go almost 13 dB means you will have a 13 dB margin in the SINR or SNR. So, this is the advantage that you get using FM, because FM can also give you this facility. So, it already had, we have already seen that it has a nice noise cancellation. Not only that, you can employ more things to cancel further noise. Okay. So, and that is the reason why means earlier days people used to transmit just voice. At that time probably amplitude modulation was still okay, but when people started transmitting all kinds of musical instruments, music and everything, then the means overall message bandwidth was not restricted to just 3.4 kilohertz or 4 kilohertz. So, it means went beyond that, and it went up to 15 kilohertz or 20 kilohertz. At that time if you employ AM modulation, huge amount of noise was coming in, and that was really killing the quality of the signal. So, FM came up very handy because in FM we could see more the bandwidth, better the noise cancellation. So, more clarity will get, that is what happens. Okay. So, I think we have now almost proven the strength of FM in a way. So, what next we will try to see that means from this perspective it looks like FM is all means implementation of FM is all rosy. It is just one of the best modulation technique that can happen and all those things. Okay. But means none of the story in this world are like that. So, it is not always means everybody or a particular part is always winner. So, there are some hind-side of FM. We will try to also means just if not quantitatively at least qualitatively clarify them in this particular part of the course. So, we will now try to see another interesting part of FM, which is called FM means if FM gets captured by the noise, it is very bad. So, that is something we will try to capture over here, which is called the threshold effect of FM, or it is also termed as click noise in FM. Okay. So, when that happens, if you remember when we were doing FM analysis, in one place we were drawing that phasor diagram, and we have also mentioned that probably the FM noise signal, the amplitude of the noise or overall power of the noise is much lesser than compared to the signal part. So, this is when FM does very nicely or perform very nicely. But when noise becomes comparable to the signal, that is when all the problem starts coming, okay, in FM. So, let us try to appreciate that. So, what happens if you remember that phasor diagram we have drawn. So, this was AC, which is the signal, and that is in the phasor what we have said, that is means the phasor phase is the reference. So, because FM has AC, then cos omega c t plus that kf into integration m alpha d alpha. So, that entire thing is the reference. On top of that, we were adding noise. So, noise has we have said that it can be represented as R t cos some omega c t plus psi t, right. That is something we have said. So, this is means after doing that quadrature and in phase representation of band pass noise, then we could represent it in this fashion. Okay. So, and we could see that that will be somewhere over here, where this angle is this psi t minus that phi t, whatever FM phase is where that FM modulation term comes. So, that phi t is actually kf integration minus infinity to t m alpha d alpha, right. We have discussed that. So, this becomes that psi t minus phi t, right. And on top of that, this is actually the R t, and that is R I t, and that is actually R q t, right. This is the overall noise plus signal, okay, phasor, and this is something we have characterized, that is the x t, right. Now, let us say what will happen to our FM. Okay. So, suppose around this I start, means what will happen, this noise is uncorrelated and it is independent, and it is probably one of the most random things that is happening. So, this noise amplitude as well as the angle will keep on varying, this will almost remain the same, whereas on top of that this will be varying. So, this tip wherever it is, this tip will be wandering around that tip, okay. It can be anything depending on how the noise amplitude is. So, this may wander within this circle probably, okay, and the amplitude also might slightly become bigger or smaller, but as long as this amplitude R t is much lesser than AC, whatever wherever they wander, they will be remaining very close to this particular point only, that x t only, okay. So, they might wander around, but they will remain over there. So, basically the phase, as you can see, overall phase will not be deviating too much, okay, because they are small in amplitude, they are varying on that location, wandering around that location. So, overall phase will still be joining some point over here, random point over here. So, the phase does not get changed hugely. So, basically if I just track the phase, it will be wandering around that value. So, this is probably that theta t. But what will happen if this amplitude becomes bigger? Then the circle that it actually wanders around is becoming much bigger, and then what might happen, we will see probably in the next class, that what might happen, that might really create a huge amount of effect in the phase variation, and the phase variation is actually that is the theta t which you are trying to track, where the FM is modulated. Differentiation of that is actually the demodulated signal. So, if this varies a lot, there will be some impulses which will be generated. So, these impulse noises are actually termed as click noise, we will see that. So, if noise amplitude is very high, then probably whenever if you are demodulating FM, you will be seeing those clicking sound in between randomly happening. So, that is actually termed as FM noise, okay, FM click noise. So, we will discuss about that in the next class, more on these things, and then we will also talk about threshold effect. Okay, thank you.